Part two of the cardiovascular system is going to focus on blood vessels. So blood vessels, which are a delivery system of structures that begins and end at the heart. So it includes the arteries, which are the ones that carry blood away from the heart, the capillaries, which are the smaller uh, branches of blood vessels, which are in direct contact with the tissues. And then there's veins that carry blood towards the heart. So a good way to remember the difference between these two is arteries starts with an A, so they're the ones that take blood away from the heart. Blood flow is the volume of blood that's flowing through vessels, organs, or the circulatory system. And resistance is the opposition to flow. So it's the peripheral resistance to flow. That's the amount of resistance that the inner surface is having on the fluid itself. And the important sources of resistance are fluid viscosity, or I should say blood viscosity. That's the thickness of blood due to the formed elements and the plasma proteins that are located within the blood. And there's total blood vessel length, okay? Because the longer the length of the blood vessel, the more resistance it'll have. Blood vessel diameter, the smaller the diameter, the more resistance the, the, the vessel will have. Okay. So you can also just think about when you're drinking something thick, like a milkshake. Um, Usually you use a shorter, wider straw, right? Because the shortness is going to offer less resistance compared to a longer straw, and also the wider diameter is going to offer less resistance compared to a narrower diameter or a smaller diameter. Blood pressure is the force per unit area that's exerted on the wall of the blood vessel by the blood, and it's expressed in millimeters per mercury. So it's measured as a systemic arterial blood pressure in large arteries near the heart. The pressure gradient provides the driving force that keeps blood moving from higher to lower pressure areas. Blood flow is directly proportional to pressure gradient. So the change in P here, that's the change in pressure. So if the pressure increases, the blood flow is going to speed up. Blood flow is inversely proportional to the peripheral resistance. So that means that as one goes up, the other one's going to go down. So in this case, if the resistance increases, the blood flow will decrease. Resistance is more important in influencing the local blood flow because it's easily changed by altering the blood vessel diameter. Systemic blood pressure, this is the pumping action of the heart that generates blood flow. The pressure results when the blood is opposed by resistance, and the systemic pressure is going to be highest in the aorta, and it's going to decline throughout the pathway. So you're going to see the steepest drop occurring in the arterioles. Arterioles are just the smaller branches of arteries. Okay, so here you can see the aorta, that that's where you find the highest pressure. And then as you're moving away, so as the aorta branches into arteries, the pressure is starting to come down. And then those are arteries branch into arterioles. Pressure keeps going down. Okay, it goes down. Then there's the capillaries where the exchange of nutrients occurs, or it could be oxygen or things like that, carbon dioxide. These are the blood vessels that are connected to the tissues themselves. Then venules are the branches that come off of the capillaries, or I should say they combine from the capillaries. And then there's those venules combine to form larger veins, and then the veins combine to form the vena cava. The mean arterial pressure is the pressure that propels the blood to tissues. So the pulse pressure phases out near the end of the arterial tree. So as you can see here, so near the end of the arterial tree, that's when the pressure starts to decline rapidly. And the mean arterial pressure is calculated by adding the diastolic pressure plus 1/3 of the pulse pressure. So if let's say the blood pressure is 120/80, 120 being the systolic pressure, 80 being the diastolic, the way you calculate the mean arterial pressure would be to subtract um, the systolic uh, or the diastolic from the systolic. So 120 minus 80, that's 40. And then you use this formula. So diastolic pressure, that's 80, plus 1/3 of the difference between the two pressures, which is 40. And then that'll give you the mean arterial pressure. So it adds up to about 93 millimeters of mercury. And the pulse pressure and the mean arterial pressure both decline with increasing distance from the heart. To measure the systemic arterial blood pressure, you can use an oscillatory method. So this is using the sphygmomanometer, and the way they do this, well, actually, you did this activity in lab. You use the cuff, you wrap it around the arm, just above the elbow or the bend of the elbow, and then you increase the pressure in the cuff until it exceeds the systolic pressure in the brachial artery, and then you're going to release that pressure, and you're going to listen for the sounds, which are called the Korokov sounds, with the stethoscope. Systolic pressure is normally less than 120 millimeters of mercury, and then systolic pressure is going to be the first sound that occurs as the blood starts to spurt through the artery. So once you release the pressure, that's going to be the first sound that you hear. Diastolic pressure is normally less than 80 millimeters of mercury. This is going to be the sound that's going to be it's the last sound before it disappears, because the artery is no longer going to be constricted by the sleeve. So capillary blood pressure that ranges from 35 millimeters of mercury at the beginning of the capillary bed to about 17 millimeters of mercury at the end of the bed. Just remember, the capillary bed is the site where the exchange occurs, like the exchange of nutrients or the exchange of oxygen and carbon dioxide. It's where the blood vessels connect to the tissues or are in contact with the tissues. Low capillary pressure is desirable because if there's too high of a blood pressure, it would rupture the capillaries, which are very thin walled. And most capillaries are very permeable, so the low pressure forces the filtrate into the interstitial spaces. Venous blood pressure changes very little during the cardiac cycle. The small pressure gradient is only about 15 millimeters of mercury. So if a vein is cut, the low pressure of the venous system causes the blood to flow out smoothly. As opposed to an artery being cut, that's when the blood spurts because the blood pressure is higher. So that's why when you donate blood, they take blood from your vein, not your artery. That's why in the movies, when you see someone, like if they get their throat cut, if like one of the major arteries is cut, like the carotid artery, that's why you see that big, you know, spurts of blood because it's under higher pressure. Low pressure is due to the cumulative effects of the peripheral resistance. So that's the resistance that's within the blood vessel, like on the inner surface of the blood vessel. And the energy of the blood pressure is lost as heat during each circuit. Low pressure of the venous side requires adaptations to help the blood return to the heart. Okay, those adaptations include the muscular pump. That's when the muscles that are around the veins, uh, when they contract, they're going to they're going to add more pressure to the vein, so that's going to push the blood upward back to the heart. So this could be um, in places like your legs, like when you constrict your calves, or when you contract your calves, I should say, that's going to increase the pressure that's applied to the veins in your leg, and that's going to help push the blood upward. And there's also these venous valves. So veins um, do have these valves, and so that's something that arteries don't have, are these valves to prevent the backflow of blood. Then there's also the respiratory pump. When you inhale, you decrease the pressure in your thoracic cavity, and you increase the pressure in your abdominal cavity. As you can tell, just when you inhale deeply, your abdomen gets narrower and your chest gets wider, right? So when you increase the pressure in your abdominal cavity, that applies more pressure to the veins in the abdomen, and so that helps push the blood up because you're decreasing the pressure in the thoracic cavity. That's going to allow for the blood to be uh, pulled upward or sucked up by the decrease in the pressure in the thoracic cavity. And then there's the sympathetic vasoconstriction or venal constriction. That's the constriction of veins that's caused by the sympathetic nervous system. All right, so that's going to do it for chapter 19. Until next time.